Fabio, you're muted. I think you're muted.
Sorry about that. Let me start again. Sorry for that. Hello again to everybody. We are pleased, me and Timo, to welcome you to the June 26th morning session for icgt 2020. The first session will be on novel formalism, and Detlef Pump will be in charge for the chairing this session. We have also a very packed day also today. We will end up around 5:30 in the afternoon with some concluding remarks that could be kind of sum up and a few other things, right, Timo?
Right. So we got a little bit of feedback yesterday, and it seems that yeah, most of you are happy with the format. The only thing that is really missing is kind of more interactive discussions, and it's the question popped up whether it, let's say, more social kind of discussions. So we have the formal questions for the talks, but the socializing is somehow missing. So the question popped up whether it would be possible to have kind of a Zoom meeting right after the closing session and sit together for a while. That was the question. We can certainly do that. So I'm taking care of installing a Zoom meeting, and then we will see how much of you are still there. Everybody can drop in and out based on personal preferences, time, and whatever. Also, one more remark, it's really worth to stay until the closing session, because it's the closing session where we will also present the best paper awards. So there are actually 2 of them. More on this later. And yes, I think that's what we wanted to say for tomorrow. This will be done in the closing session, and I think until then we have a tough program. So I don't want to spend more time on providing more information. Let's have an interesting day 2 of the conference. And I think Detlef, you may start with the session chairing of the first session of today. Unless I forgot something, Fabio.
No, I think that we can make available the Zoom link directly on the online program page, right?
Yes, on the online program page or in the chat. We will see. We will manage to distribute it somehow.
Okay.
Nobody will miss it.
Very well.
Thank you, Fabio.
Then I think fine. Now I'll remove myself and Timo from the stream, and I will add Harald just in a moment. Okay. And good day to everybody. Bye.
All right. Okay. So good morning, everybody. Also from me, I have a little problem here with my screen. Timo's picture is frozen, but I hope everybody can hear me. Can you hear me? No.
Well, I can hear you.
Damn.
Yes, we can hear you. Let me see what people is. Yes. Go ahead. We can hear you. Okay. This is a bit unfortunate. Even if I think I can do the. Can I say I can fit in Detlef's shoes and try to do the anyhow, the preliminary introduction for Harald. The schedule and the timing will be the one that Detlef set, but I think that we can easily start now. Let's see if Harald, are you ready?
I am ready, and I hope everyone can hear me.
Very well. So
Okay.
Yes, sure. So let's wait for a moment until Detlef is back. Apparently no. So, well, Harald, I think you can start. I will take myself out of the stream and I'll try to add Detlef as soon as he's back. Oh, here he is.
Okay. Can everybody now hear me, Fabio?
Sure, absolutely.
So maybe
everything is fine.
Maybe I take over then. Apologies to everybody. Something with the internet connection went wrong. I hope it will be better now. So without further ado, Harald, just go ahead.
Okay. Thank you, Detlef, and thank you for the invitation to this conference. I'd like to present joint work with Patrick Stünkel from Høgskolen på Vestlandet, i Bergen in Norway. And we want to dedicate this talk to Michael Löwe, who many people in the audience knew very well, and who passed away in December 2019. He was an extraordinarily committed teacher and a scientist, and we will all miss his progressive attitude and his innovations. As a researcher, he introduced me into the community of graph transformation people, and I must say that without him, I would not be here today. So amongst the wide variety of his research topics, there were two central research topics that he was working on. One, of course, as everyone knows, was the single push-out approach, the main topic of his PhD thesis. And the second, where he was also working on quite intensively, were partial algebras. That was a work that he carried out later on. So we thought that for this conference, we should submit a paper which, to a certain extent, deals with both of these topics. And so as you can see in the title, single push-out in comprehensive systems, then SPO is the first part of his work that I mentioned. And these comprehensive systems, I'll explain in a minute, are to a certain extent partial algebras. And we thought it would be a nice combination in order to, to have a tribute to Michael here. So to make a transition to the content of the talk, let me start by explaining what comprehensive systems are. The background of these systems is multimodeling. I hope that this slide about multimodeling can be viewed now. Yeah, is it okay? Is it viewable?
The font is a bit small in the picture, but otherwise...
No problem. Okay, you see it. Okay, you don't have to read the details in the picture. Thank you. So the background of these comprehensive systems that I want to talk about is multimodeling. As you can often experience in larger software projects, you have a bunch of overlapping conceptual models, as can be seen in the top of the picture here, where you don't have to read the details. And these models focus on different aspects of the system. And of course, they are designed by different teams. So you have requirements artifacts, you have code, you have class diagrams, BPMN diagrams, and so on. And the question is, how can one manage the global consistency of these artifacts if there is a local evolution? A local evolution means that if you change the class diagram, or if you change the code, or if you change anything else, how can all the other models be adjusted such that the update is propagated in a consistent way to the other models? So the question is, how can one define constraints? How can one verify constraints? And then the question we wanted to deal with here is how can consistency restored in a somehow semi-automatic way. So that's the topic. And the problem statement of our paper is we want to enable a global consistency management of a multi-model. That is global consistency management of a bunch of models. And we want to do it rule-based. So there are different approaches to do that. One of that is rule-based, but there are also other approaches like search-based mechanisms, and recently also mechanisms that are based on machine learning. But here we want to go for a rule-based approach. Here is an example what could happen. You can imagine that there are three class diagrams being developed, for example, by different developers. And for all of these developers, their class diagram looks perfectly fine. But if you take a look at these three class diagrams together, then there's a cycle in the inheritance relation. So the problem is here, how can we find that out? And in the end, how can we repair this problem? A second example is not on the model level, but it's on the instance level. We have three systems on the right-hand side, A1, A2, and A3, and you can imagine that those are three databases in which person records are stored. In the first system, a telephone number is stored with a person record. In the second system, a home address is stored. And in the third system, in addition to that, a company is stored where the person is working. And we might have a constraint saying that persons with business addresses must have phone or home address. So what we need here, and that's the central topic of my talk, we need commonality specifications. That is, in order to decide whether these systems, taken as a whole, are consistent, we need to specify which of the entities in the different systems are actually the same. On the left-hand side, there's implicit sameness because of the names of the classes. But on the right-hand side, with the persons, there might not be an explicit way of identifying the persons. Maybe there are different information stored. Maybe, well, there may be typographic errors in the names and so on. So you cannot identify them by their features. So you have to add a graph in the middle, A0, which specifies this sameness. So we see with the node 1 here that there's a sameness specified saying that the three persons in these three systems are actually the same person. There is a node 2 which specifies sameness of the home addresses. Yeah, and there's an edge 3 which specifies sameness of the links between the persons and the home address. So what is important here? We have to unify different kinds of relations. Like the first one with the node 1 is a ternary relation, and the other two are binary relations. Okay, so let's keep in mind we have commonality specifications between these three different systems. So how do we define comprehensive systems then? The idea is simple. We take a base category, we call it G. It's just, let's say, it's a category which contains algebras based on signature with unary operation symbols, like graph-like structures, simple graphs, or e-graphs, and so on. And let's say that we have a number n, which actually specifies the number of artifacts to be kept in sync here. So the definition of comprehensive system is simple. It just says a comprehensive system is an n-tuple, which consists of n partial morphisms. You see them here, with a common domain. So these partial morphisms have as a domain the commonality specifications in the middle, so the gray part here. And so we specify these samenesses by saying we have a partial map from A0 to A1, we have a partial map from A0 to A2, and one from A0 to A3. Note that partial maps are encoded in the usual way. So they are spans with a left leg monic, and of course with respect to a certain equivalence relation, which specifies that two of these spans are equivalent if there are two middle objects are isomorphic. Okay, so those are comprehensive systems. Why are they a partial algebra? you can encode this entire structure up here with a single algebra by internalizing the partial graph action here. But that's something I don't want to go much into detail. Okay, so let me just give some hints to related work, because some of you, for example, the triple graph people may know all this story. But the first hint here is that these commonality specifications were already informally used in many practical approaches. You can mention many names like Manuel Wimmer or Alexander Egget. They use these commonality specifications by just drawing lines from one model to another model, saying, okay, these are somehow parts of the models that depend on each other, and they do something like a linguistic extension. For the formal background here, of course, I have to mention triple graphs. But triple graphs they specify binary commonalities with total morphisms. So we have a kind of generalization here of triple graphs. In the multi-ARI case, it has been shown that a family of binary relation has not enough expressive power to express the things that we want to work with here. As I showed before, you need a ternary relation and a binary relation, and so it's a little bit more complicated. So we cannot work with binary relations only. And in the multi-ARI commonalities, there's a generalization of triple graphs called graph diagrams by Frank Trollmann. But it turned out that these structures are somehow complicated because the underlying shape is more complicated. It specifies every kind of relation that you need. It specifies binary, ternary, and multi-ARI relations, and so you get a complicated structure then. So we introduced comprehensive systems in 2018, and in 2019, in a paper of icgt last year, there was like Jens Kosiol and others picked up this idea. No, they not really picked up. They had the idea on their own, of course. The so-called S-Cartesian categories, which are a generalization of the idea of having partial maps within the whole structure, and they needed this theory because they wanted to deal with triple graphs with partial maps. So what they did is they invented a category with S-Cartesian objects, and actually this category is more general than our comprehensive systems. But what they did in their paper was that they lifted DPO properties, like adhesiveness of the base category, to these compound systems. What we want to do here is we want to lift SPO theory from these graph-like structures to comprehensive systems. Okay, so let's take one of these typical use cases where the problem occurs of that a rule, a graph transformation rule, might help to restore consistency. Imagine the system looks like here on the left-hand side with one person, like you see two persons, but they are specified to be the same. And then someone adds the company where this person is working on. He can add it only in system G3 because these companies are only recorded in the system. And because now the constraint that we had, that persons with business addresses must have phone or home address, is violated, we also need to add in the second step the phone number here. But we can only add it in the first system, because in the first system, phone numbers are recorded and not in the other systems. So now the question arises, how can we probably automatically add, or let's say extend the relation? Because if we add this person record, which is actually the same than the records of the persons below, and we need to extend this binary relation to a ternary one. And the hope is, can we do it with a graph transformation rule? And in our case, the hope is, can we do it with a single push-out graph transformation rule? So extending this commonality relation is the topic here. And the question is, in which category are we working? And has this category push-outs with respect to partial morphisms? Yeah, so only if it has push-outs, then we can enable single push-out rewriting. So we had to design a category. The objects are there, so we know how they look like. And I said before that they are somehow, to a certain extent, they are partial algebras. This is our bunch of partial algebras which make up the comprehensive system. The question then was, which morphisms do we define in this category? And the first attempt was we just take morphisms which preserve definedness, which is the classical way of doing it. And all the people who are working with partial algebras know that these morphisms are called weak morphisms in this case. When we were working with it, we found a counterexample that in this category, push-outs with partial morphisms may not exist. I don't want to go too much into detail of this example, just wanted to show it. It's very simple. The comprehensive systems are shown here in brackets on the left-hand side. So this is a comprehensive system with n equals 1. So very simple. The star is an element in this commonality specification, and the bullet is an element in the component A1. And if you construct a push-out, without going too much into detail here, of a total map, but if you do it in the category with partial morphisms, you construct the push-out F with itself, then you can find out in this picture that the push-out doesn't exist in the category with partial morphisms. And that was kind of a very sad result because, yeah, we couldn't go on working. But we thought of, can we change the setting here? Can we somehow move to a different set of partial morphisms? No, sorry. Can we go to a different set of morphisms which makes up the category CS of comprehensive systems, such that single push-out rewriting is possible? And indeed, we found out that we can use closed morphisms. So what are closed morphisms? It's nothing else than saying that definedness is not not only preserved, but it is also reflected. And the question, this equation is shown here. The partial morphisms, whenever they are defined, then they are then the partial morphisms in the image AI prime is also defined whenever for F0, yeah, for the zero component, for the component of F, which works on this commonality specification, and this is an equivalence, right? So we used to we changed to closed morphisms and asked the questions whether this is okay. Can we adhere to this definition? We found out that actually this category has no products, no terminal objects, so this was somehow a problem. But then in a further investigation, we saw that we have pullbacks and that this category is actually co-complete. It has all co-limits. And many of the constructions and also properties like monomorphisms carry over from the base category G to these comprehensive systems component-wise. So this is the typical way of the typical chance of lifting properties from a base category to this compound category or to functor categories, as many of you are working on as well. And so we hope that we can go on with this in a better way. And actually, if you think about moving from a category with total morphisms to a category with partial morphisms, and you think about push-outs, then immediately you come to the question whether the category CS is hereditary. Hereditariness means just that the embedding functor, which maps a total morphism to the partial morphism with an identical left leg, that this functor preserves push-outs. And indeed it does. So the category CS is hereditary. And by the way, that's what we also could state here, the category CS is a recursive HLR category, which was already shown in the Corsiol paper in 2019, so that was nothing new here. But the most important fact is CS is hereditary, right? So that gave us the chance to think about, okay, what do we have to do in order to find out whether there are push-outs with partial morphisms? So a push-out with partial morphisms looks like in the right-hand side here. We work with total matches, yeah, so that's enough for us, but the rule from L to R could be a partial morphism. And obviously, in some cases, as you know, the co-match mu prime might then be partial as well.
Harald, about 5 minutes left.
Okay, thank you. So the question was, are there push-outs in the category of partial morphisms? And it turned out that was kind of difficult to lift properties because it is not working in the same way as lifting properties like adhesiveness from the base category to the bigger categories, like as can be done in the double push-out view. So we needed a theorem, the theorem by Jonathan Hyman and Tobias Heindl here, which said, okay, if you have a category, any category C with pullbacks, then the category with partial morphisms has push-outs if and only if it is hereditary. Here we go again. And if it has inverse image functions, if the inverse image functions have upper adjoints. So we know already that C is hereditary, and so we had to check whether there are upper adjoints of inverse image functions. So just a short idea what upper adjoints are. Upper adjoints of inverse image functions. So I have to first I have to explain what inverse image functions are. You take in a category with pullbacks, you can take an object A and consider the subobjects of A, which is a semi-lattice because it has a meet due to the pullbacks. And then the inverse image function is just using the pullback, taking a subobject of B and assigning to it a subobject of A via pulling back. So that's the inverse image function. And an upper adjoint is something like saying, okay, I look for, or given a subobject of A, so I want to have something like an inverse of this inverse image function. Given a subobject of A, I'm looking for the largest subobject under B, such that its inverse image is still under the given subobject of A. And that's what this equation tells us. So that's the definition of upper adjoint. For all of those who know that the concept of right adjoints of pullback functors, the upper adjoint concept is a special case of the adjunction equation of the left and right adjoint adjunction of pullback functor with its right adjoint. And actually the equation here says again what I said before. You get the upper adjoint if you consider the join of all subobjects of B, whose inverse image is still under N. Fortunately, while we find out that in our category CS there are upper adjoints, and I don't want to go into detail how that works, such that the theorem of Hyman and Heindel guarantees us that our category of comprehensive systems admits all push-outs with respect to partial morphisms. So that was very good. And we can now apply this result to this example that I gave you before. You can remember that we added here in this host graph, that we added the company the person is working on. And in order to restore consistency, we also had to add a phone number, which could only be done in this system. And now what has to be done in conclusion with that is we need to update the binary relation here, the binary commonality relation, to a ternary one. And we can do it with a single push-out rule. The rule looks like this on top here. It's called rho. It is undefined on the red spot, such that in the push-out, the binary commonality relation is deleted and a ternary one is added. And that worked really fine. So we could imagine that a rule in the end restores consistency again, saying, okay, these 3 person records are exactly specify the same person. So that was really nice. And an advantage of this rule is that if you take a look at how it works, it cannot be applied twice. So if you would try to apply this rule with a match from L from the left-hand side to H now, you would fail because there is no morphism from L to H due to the reflection of the findness. Yeah, the red spot cannot be mapped here because the partial map from H0 to H1 is defined here, and here it is not defined. So that was a nice.
Sorry, but you need to come to an end.
1 minute.
Okay.
Yeah. So there are also disadvantages. Okay, I don't go into details of disadvantages because of the time, and come to my conclusion. So we hope to define a reasonable set of SPO rules for global multimodal synchronization and repair. We can imagine that maybe we can generate rules on these more compound systems from model repair rules that are defined on, let's say, merged systems. But that is something if I would explain it, I need 10 more minutes. And obviously, there are many open issues, like we don't know how to manage typing. That's a bit difficult because these morphisms, or these typing morphisms, must be cannot be closed. We need criterion for conflict freeness, and we need to fully work out the SPO potential. So my last statement here is, and I apologize for being a little bit too long. My last statement is that the contents of our paper should rather be considered a starting point than the final document of this research issue. And that's the sentence. And I wanted to cite the last statement in Michael's PhD thesis, because that's exactly what he said in the end of his PhD thesis. So in this spirit, I'd like to go on with this research topic here, and also being in memory of Michael Löwe. So thank you for your attention. I'm open for questions.
Okay, thank you very much, Harold. I don't see any questions right now on the live comments, so I think I would suggest, because of the advanced time, that we just carry on with the program.
Okay.
So if the next speaker is there, or I'm not sure, do we first go to Fabio? There's Tikon. Tikon, are you ready? Can you share your slide?
Oh, but my talk is on, well, 12 o'clock.
Oh, no, you are not yet. So it's Roy. Sorry, that's my fault. Is Roy there? Not yet.
I was too fast.
Yes. Hi.
No, there he is. There he is. Hi, Roy. Can you share your slides
Screen.
and just go ahead, because we are a bit over time?
Yes. Okay, is it working?
Not yet. At least I don't see it yet. No, it's coming. Yeah, perfect. I can see it.
Perfect.
So please go ahead, Roy.
All right, so I'm presenting patch graph rewriting, which is joint work with Jörg and Trulis. So let's start with a typical difficulty in graph rewriting. Let's say I define this rule on the left here, which intuitively specifies the deletion of a cycle of this shape. Is it still working? Sorry.
I can see it at least.
Okay, sorry. The sound changed for me. Okay, sorry. If you start with this rule on the left, you want to delete a cycle of this shape. And now you want to apply it to a larger graph such as this one. Now you cannot outright apply it, because when you do that, these red dotted edges would be left dangling. So for any formalism that you define, you have to answer one or two questions, namely, is the application allowed? And secondly, if it's allowed, what should be the result of this rewrite step? So two very well-known examples are DPO and SPO. So DPO would say it's not allowed because you can only apply a rewrite rule if it doesn't leave dangling edges, and SPO says there are no application conditions, you can always go ahead, and the result is simply that the dangling edges must be deleted. So these are two examples of quite coarse-grained solutions to this problem. And the key idea of our paper is that we wanted to specify, wanted to be able to specify such policies at the level of this rule. So introduce some kind of flexibility specifically for this kind of situation. So let's start with some terminology which is helpful and which explains the title of our paper. Let's say we have this on the left. This is called a pattern as usual, and you find the match in some host graph here in green. Now, what this induces in the host graph is a decomposition as follows. We have a context here, which is considered a part of the graph, which is not part of the match and also not touching it, so to speak. So it's completely disjoint for it. So it's a bit more restricted meaning than might be usually the case. And then we distinguish specifically this notion of a patch in red here, which contains exactly those edges that are left dangling. So you can think of it as a set of edges where the edges go from the match to the context and the other way around. And also the edges can be defined purely on the match graph itself. So you can think of it as a set of edges or as the smallest graph containing those edges. Both viewpoints are fine. And so, yeah, I've explained the idea, and we have one specific implementation of this idea, and it's called patch graph rewriting with a big P. It's characterized by a visual and we think intuitive notation. It is very lightweight set theoretic formal semantics, and it's defined specifically for edge-labeled multi-graphs. So we really went for a kind of simplicity which we think is good for accessibility and for for a kind of prototypical exploration of this idea. So in the remainder of this talk, I will explain the semantics of PGR. I show an example where I model weight-4 graphs and I compare to some existing frameworks to help you situate the framework. Let's start with an intuitive explanation. So on the left, I show a PGR rule, and on the right, its application. If you look at this rule, it applies to the singleton node here with the A loop, and this induces the patch in red here. And so the question is, can this rule be applied in PGR right now? And if so, how are these patch edges handled? And in PGR, the left-hand side here, the left-hand side of the rule specifies implicitly that the patch must be empty. So specifically, you can only apply this rule to a component graph which consists of just one node and an A loop. So what if you want to make it applicable? Then you introduce annotations of this kind. So they're called patch type edges. The patch type edge labeled with 2 can be thought of as allowing patch edges coming out of the node with the A loop, and the patch edge labeled with 1 similarly can be viewed as allowing patch edges that enter the A loop. This kind of annotated pattern, we introduced terminology scheme to disambiguate it from the pattern, which is this inside part. And then in the application, we speak of adhering patch edges, which are the kind of patch edges that kind of get caught by these annotations. And in this case, the read step is as follows. Since the patch type edges are not reused, adhering patch edges are deleted. So you can think of it as the kind of variables you might see in term rewriting. So you can reuse them or not, except that I should clarify that this stands for 0 or more patch edges. So it's also fine if there are no patch edges. So as I indicated, you can reuse patch type edges on the right, and then the patch edges are reinserted. And also you can see that incidences to nodes in the context are preserved if applicable. So this patch type edge labeled with 1 was incident to this node here, and also over here. This is still the case when we reintroduce it into the right-hand side. What other things can you do? You can also replicate type edges, and then simply the adherents are replicated in the right-hand side as indicated by this picture. You can invert patch type edges. So over here, the nodes are incoming to the node labeled with A, and now they're outgoing. This is fine. We just remember the incidence to the context. And also you can see here this patch type edge is kind of pulled into the pattern, whereas before it was going out into the pattern, and this is also fine. Then there are loops in the host graph. They are just dealt with similarly. So now in this host graph, I've introduced a loop labeled with F. You can similarly, if you want the rule to be applicable, you have to introduce an annotation, and it also gets bound to it. It bounds the corresponding edges. And this rule in particular then, it shows a kind of cloning of nodes where the loop labeled with A is simply deleted from both clones, and you get this result. Okay, so this is now all very intuitively explained, but what could possibly be a sane semantics for a rule like this one, where we capture patch edges that are between 2 nodes of the match, and then we send it out into the context. Your instinct might say, well, we could maybe say that this is non-deterministically selected where it goes to, but for some matches, there might not even be a context. So we simply forbid it, and we make that precise in the formal semantics, of which I will now give a kind of bird's view. So first of all, we have this notion of a patch type. So here's the graph G, and a patch type for G are the red dotted edges. It's an unlabeled patch for G and the trivial graph consisting of just this context node. So since it is a patch, you can have edges to it, from it, and on G itself. So the asymmetry is in that you can add edges to G, but not on the context node. And if we simplify notation, since we only use one particular context node, we can also write it like this, letting it be understood that if something is not incident to a node, then it's incident to the context node. And the numbering you saw on the earlier slides will be introduced in a little bit. A scheme then is a graph P, the pattern, so G in this case, and a patch type for that pattern. Okay, so now we can define what a patch graph rewrite rule is. So it's just a pair of schemes as previously defined. And it comes equipped with trace functions relating the right patch edges to, the patch type edges to the left patch type edges, saying how they are, how it's considered the rearrangement of the part on the left. And in pictures, we depict that using this numbering system. We have an additional constraint for every patch type edge on the right, such as this patch type edge labeled with 3. If it's incident to the context, we require that it's also incident to the context on the left, so that you can always sort of load the context node if needed. So that in particular excludes the weird example I ended with the intuitive semantics. And moreover, we require that this left type graph is simple. Now, why do we do that? Suppose you drop simplicity. So now we have two unlabeled patch type edges between two nodes. Let's say I find this graph, I can make it match, but now I have a choice on how I want to make these patch type edges adhere. And in the rewrite step, which I will define after this slide, this means that you can choose which edges you want to bind to 2 and which edge you want to bind to 1. In other words, this rule allows deleting an arbitrary subset of patch edges between two nodes. So we have some kind of non-determinism, and in our paper we call these quasi-rules. When comparing to frameworks, that have non-deterministic effects, they can be interesting, and also if you make extensions, they can perhaps be interesting if you control the non-determinism. But for our setting, we like the determinism, so we add the condition. So now I will give a big picture view of the rewrite step. It's fine if you do not catch all the details here, because they will not matter in the sequel, but then at least you know a bit what's going on under the hood. So a rule, as explained, is a pair of schemes which satisfies minimal conditions. And it comes equipped with trace functions from right to left, which establish a relation between the two patch type graphs. Now, if we want to find a match in a graph, we use the pattern of the left scheme to do that, which induces a patch decomposition of G, always uniquely. So in this case, the patch J is indicated in red and the context C in black. Now, for the rule to be applicable, there needs to be what we call, and it is applicable in this case, there needs to be what we call an adherence map. So I will not explain the details, but this map ensures that every patch edge is, every map from a patch edge to a patch type edge is proper in a sense. So this binds these patch edges to the patch type edges. Then a reduct is defined as consisting of just the context C, you copy it over, and rather than the match PL, you enter the match graph PR from the right scheme. And the patch K is then defined as follows. The patch looks like this in this case. It must adhere to the right type graph through some adherence map. So this ensures that, for instance, you cannot add junk on the side that shouldn't be there. And in addition, it needs to be full enough. So for every patch type edge on the right, it has to intuitively copy over the patch edges from the left. So more formally, for every type edge on the right, the two pre-images of the adherence maps must be isomorphic, so they must have the same number and the same kind of label distribution. And there's some additional condition which I don't show here, which basically means that you also have to ensure that the connection to the context is proper in a case like this one. But that's the general idea. So now I will show you a use case example where we use it to model weight-4 graphs. So vertices represent processes in a weight-4 graph. And weight-4 graphs are traditionally defined for hyperedges. So you have a hyperedge from a node P, a process P, to K processes, which represents an n out of K request for n resources where n is bounded by the K. So it's fine with getting less resources than it requests. And processes have at most one outgoing request. This is an invariant. So here's an example of a hyperedge with a 2 out of 3 request. And we encode them, since we're in the setting of edge-labeled multigraphs, we encode them as follows. The counter has a loop with Z representing 0, and then an S loop for every +1 or increment to that counter. And we make this property over here invariant. So a process is a loopless node, and a counter is a node with at least one loop, which is also why we added the Z node to ensure that always it has some kind of loop. All right. First of all, I'll show you how we can define a complete grammar for weight-4 graphs, starting from the initial graph. The empty graph is the initial graph. We have a rule for process or node creation, which can be applied at any time. And then we have a rule for creating a 1 out of 1 request. So in this case, this process, it can have incoming requests and outgoing requests. And we know it's a process because it doesn't have a loop. And this process, it may have incoming requests, but it does not have an outgoing request yet. So now it's allowed to make a 1 out of 1 request to this node, and the counter is set to 1. And in the grammar, we can extend such requests. We keep the counter the same, and any targeted processes, these connections are just kept, they are remaining. But now we are allowed to introduce an additional process. Again, it's loopless, so we know it's a process. It can already have incoming and already an outgoing request, but we can involve it from the perspective of 1. So we extend an n out of m request to an n out of m+1 request. And we have a rule which is exactly the same, except now also we increment the counter. So we extend an n out of m to an m+1 out of m+1 request. So this is a grammar. Any valid weight-4 graph can be generated using these rules, and conversely, any weight-4 graph you generate, any graph you generate is a weight-4 graph, but it doesn't model the dynamics of a distributed system because there is some kind of dynamics associated with these weight-4 graphs. And we can model that as well, which I will do now, and I will explain the dynamics as I introduce the rules. So we assume that processes can be created or they can join at any time, depending on your perspective. But also processes can leave. So this is the inverse of create. But now, since there are no patch type edges, there is an application condition which says that the process cannot have a pending outgoing request, and it can also not be targeted with requests. So it really doesn't harm if it leaves. Then n out of m requests are made atomically in the actual dynamics of the system. You can of course model this with an atomic sequence of steps shown before, so 1 out of 1 requests and then a number of suitable extensions. It could be interesting to look how from such a sequence you can generate a single rule, which is something that's typically studied in graph rewriting, but we don't have anything research in that direction yet. Then there is the rule grant, which is used for granting a request. So the idea is that a process, this top one over here, when it is unblocked, that is, it has no outgoing request, it is allowed to grant a request. So the connection is deleted and also the counter is decremented, as you can see in this picture. And for the rest, it stays the same. Now, when enough grants have been applied, at some point the counter will be 0, so it just has a Z loop, and still an incoming request, and maybe still a bunch of outgoing request edges in case the n was smaller than the n in the n out of n request. But then this gets resolved just by deleting the node and all the incident patch edges. Now this, so far this is kind of the standard dynamics associated with wait-for graphs, and to make it a little more interesting, we will add some idea of load balancing. So to just show you an example already, in this case, let's say this process is considered overloaded because there's more than 2 requests. What we do then is we create a clone, and it inherits all the requests except 2 of them. Now you might notice that there are no patch type edges here, and we shouldn't really care what the counter looks like. And implicit here is a kind of meta notation, a shorthand notation that we explain in the paper. But the idea is that for these labeled or named nodes, the complete patch type graph is induced between them and the context node. So this ensures that their surrounding is no constraint on the application or applicability of this rule. Okay, and this is in the case where the process is unblocked, as you can see. So what if the process is blocked? Well, the assumption is, of course, that a process can only grant when it's unblocked, because it might need the resource itself before it can answer requests. So in this case, we also we do the same, but we also duplicate the outgoing request as follows. All right. That leads me to the comparison. We are more exhaustive in the paper, but I will just give you some idea here. So let's say I have this double push-out rule where the numbers here indicate the inclusions in the, sorry, this is the interface, and they, as normal, indicate how the interface is included in the left-hand side and in the right-hand side. We can model this example with the following PGR rule. So we have all the patch type edges on the nodes in the interface, because that should not limit rule applicability, and they get copied over to the right. And also we have here a negative application addition that it cannot have any incident patch edges, as is usually the case in DPO. So in our comparison, we mostly focus on, let's say, reachability of graphs. And in that case, you can simulate DPO. But of course, to say that PGR subsumes DPO would be too strong, because DPO can also be applied to much richer structures than graphs, for instance. And for single push-out, for the single push-out approach, the solution is kind of similar. So if this is an SPO rule where this is the left-hand side and this is the right-hand side, and we have some partial map where this part would get deleted, all we have to do is add patch type edges around this part so that it doesn't limit rule applicability. And then on the right, we delete those patch type edges to model the destructive side effect of the single push-out approach. But again, if you were to draw this here, it would turn into a big spaghetti of patch type edges. But also here, you can use the shorthand notation that was hinted at in the previous slide.
So Roy, maybe 3 minutes left. Would that be okay?
Yeah, that would be perfect. Thank you. So another comparison that's is good to make, because for 2 reasons, is with Agree by Andrea Corradini and others. It's a very powerful algebraic approach. So it subsumes DPO, SPO, and sesqui push-out under mildly restricted assumptions. So it's powerful, but also we see a lot of similarities with this approach. So Agree allows cloning nodes, and then you might want to retain only a subset of edges that are incident to the clone node. So it has a kind of mechanism for filtering what we would call patch edges. So also here, there is a lot of, you can add some flexibility to how these patch edges should be handled. So in spirit, there are some similarities. But the two can do things different from one another. Agree, for instance, cannot express the following PGR rule, where the 6 and the 1 are intuitively swapped here in the rule. And also this negative application condition that this must be loopless, I think, cannot be expressed in agree. But on the other hand, agree can express some global transformations, and can also, as a natural mechanism for filtering edges based on their type, which PGR has no support for. And again, as before, for agree and DPO, it's easier to prove all these kind of interesting meta properties like parallelism, and also apply to richer kinds of graphs. And PGR is only defined for edge-labeled multigraphs in that regard. For the others, we've done some more comparisons. For that, I would like to refer to the paper. So we also consider an approach from the algorithmic tradition, which is very expressive, also this kind of flexibility. But yeah, for all these approaches, there is a kind of trade-off to be considered. So let me just say something about future plans. This week we actually had a very interesting discussion with Andrea Corradini about an algebraic approach to PGR, which we would like to investigate. I would also like to understand it a bit better, so that's actually interesting for me as well. And once we've settled on something, we would like to study the usual properties such as parallelism, concurrency, termination, and so on. We're also interested in adding constraint labels on patch type edges so that you can have, let's say, cardinality constraints on how many patch edges are allowed. And we are more interested also in modeling distributed algorithms, because we think it can offer a nice intermediary between, let's say, a natural language description of such an algorithm and the pseudocode description of that. And we would like to investigate how suitable PGR might be for that. And yeah, that's it. So thank you.
Okay, thank you very much, Roy. I have one question here by Barbara Koenig, which I may read out directly, I think. So she says, this looks somehow related, there it is, to node replacement graph grammars with neighborhood-controlled embedding by Engelfried and Rosenberg. You should give it a look. I'm not sure you are aware of this one, but yeah, that's a very old classical approach.
I see. I'm not sure if it's how related this to this approach by Nagel. So what Nagel, for instance, allows is much more expressive transformations than we do. So they can go deep into the graph, check for some property, and then establish.
No, usually this node, that variants of node replacement, but one basic idea of node replacement is to have a context-free version of graph rewrite, so a limited. An approach of limited power.
I see.
Anyway,
okay.
Then you may just have a look. Then there's another question by Gabi Tensor. The relation to multi-amalgamated graph transformation would also be interesting. There it is. I'm not sure you have heard of that one.
I have not, but I will note it down, and thanks for the suggestion.
Yeah, okay, so we take that as a comment. I myself have a quick question. So I think your framework is very nice, very flexible and powerful, obviously, but still quite clear. But usually, as usual, if one has powerful formalisms, the drawback is, showing properties. It gets more complicated. So, and you mentioned already, obviously, you at the beginning, and you want to look into stuff like parallelism, concurrency. So for just one simple example, double push out, let's say, parallel independence, right? Two steps are independent if you apply two rules to the same graph, if they share only interface items, so items which are not deleted, and then it's well known you can swap the two steps, get a diamond, which is important also for confluence and all other stuff. So if you look at the old DPO proof by Hartmut Erich and Hans Jorkowski, it's actually there the categorical formulation pays off because by simple categorical lemmata like existence of push-out, existence of pullbacks, composition and decomposition of push-outs is essentially all you need, and it has quite an elegant proof, whereas I think if you had to do it on a set theoretic level, in my point of view, it would become quite ugly. So any comments on that? Yeah,
we think the same. So that's the reason why we want to definitely investigate an algebraic approach. Thinking about these problems on the set theoretic level seems quite difficult. So when we started formulating it, we didn't necessarily think this was kind of a prototype formalism, but now we are leaning in that direction. So it's a very valid point, I think.
Yeah. No, I think that's fine. I mean, my personal view is also that one should have both views, equivalent views, operational, and which is for all kinds of reasons, also to teaching, for instance. It's in my experience easier. But then saying, look, there's a different equivalent view with this algebraic outer category stuff, which sometimes pays off, improves, and so on. I think one should have both. But anyway, that's my personal.
Yeah. So maybe we can improve an equivalence. But thank you.
Yeah, thanks for your nice talk. I think we should conclude here, and maybe Fabio, Tikon is already there. So Tikon, are you ready? Do you want to share your slide?
Yes, they are shared already, I suppose.
I can't. It's coming now. It's coming. Okay. Yeah. So the talk, as everybody can see now, hopefully, is about hypergraph basic categorical grammars. And I'm sure Tikon will tell us what that is about. So Tikon, please go ahead.
Yeah, thank you, Detlef. Well, I'm going to talk about a combination of two approaches, of basic categorical grammars for strings and of hyper-rich replacement grammar, that is a classical, approach to describing graph languages. Well, just to say some introductory words, there are two wide classes of grammars. The first one is generative grammars. They produce strings by applying productions. There is an initial symbol and a set of rules, and in order to check whether a string is correct, we attempt to derive it from the initial symbol by applying several productions. For instance, there are well-known context-free grammars that work exactly in this way. Well, on the other hand, there are categorical grammars, and they deal with types. So there is a uniform mechanism that explains how types, some special types, interact with each other, and a grammar is a correspondence between symbols of an alphabet and types. Well, and in order to check whether a string is correct, one tries to assign types to symbols, corresponding types, with respect to a grammar in such a way that the string of corresponding types is correct with respect to uniform roles of the mechanism. Well, and usually categorical grammars are based on some logical calculus, for instance, on the Lembeck calculus, and this means that a correctness of a string is equivalent to a provability of a corresponding theorem. And one of fundamental examples is basic categorical grammar. Well, some formal definitions. There are primitive types, and types of basic categorical grammars are constructed by using left division and right division. So, for instance, here is a type with 4 primitive subtypes. Well, and there are 2 reduction laws. Well, they say that if there are types, for instance, A and A under B, left division B, or B, right division A and A standing next to each other, then they can be reduced to B. So these are reduction laws. Yes, it is just about denotation. Well, and the basic categorical grammar, as I said, is a correspondence. Essentially, it is a correspondence between symbols of an alphabet and between types. There is also one distinguished primitive type S, and well, the language generated by a grammar is the set of all strings such that we can, assign types to symbols in such a way that a string of types, T1, T2, and so on, can be reduced by applying reduction laws to this primitive type S. So everything as in the general, scheme. For instance, we can consider the following basic categorical grammar. Well, it generates, it has 3 correspondences, and it generates the language of strings, for instance, where A's appear at the beginning n times, and then B's appear n times at the end. So, for instance, this string can be derived. We assign types to symbols with respect to this relation, and then we reduce this to S. And yes, we can do this. We start with P, S, P, S, P, and S. Well, this is it. So actually, basic categorical grammars are interesting to linguists, so because certain linguistic phenomena can be described by them. So yesterday we had a talk of Bob Koke about this. And also basic categorical grammars can be merged with the lambda calculus, and thus they can describe semantics of sentences. For example, we can consider this sentence: Tim thinks Helen is smart. Then we assign these types of basic categorical grammar to words. So this string can be reduced to S. Well, edge is reduced and P, then S, then this and P, and this S retains. And also, well, simultaneously, we can apply semantic types that are written here. We apply them to each other and obtain a the meaning think of smart of Helen, Tim. So this is a nice semantic representation of this sentence. Well, but actually, basic categorical grammars are not too strong to describe diversity of linguistic phenomena. So there are several ways in which we can extend basic categorical grammars, and we decided to try to generalize them to hypergraphs, well, and to make them somehow related to hyper-edge replacement grammars. So our goal is to fill this empty cell with a question mark, so to extend somehow basic categorical grammars to hypergraphs. So this is the main objective. Well, just to recall in very brief, we work with hypergraphs, so they have nodes, edges, hyperedges. Edges are attached to nodes. Edges are labeled. There are external nodes that serve to connect a hypergraph with other ones. For instance, here is how we draw hypergraphs. Numbers in brackets are external nodes. Well, we define the replacement of an edge with a hypergraph in a natural and standard way. Well, and finally, we define a hyperedge replacement grammar. Well, it has non-terminal and terminal symbols. It has productions that allow one to replace a non-terminal symbol with a hypergraph and the initial symbol. Well, and the language generated by a grammar is the set of all hypergraphs that can be derived from a start symbol by applying productions several times. This is all standard. So now we need a procedure that would generalize these reduction laws for basic categorical grammars. So the first thing we need is compression. It is also a quite natural transformation of graphs. So it is done as follows. Let G be a graph and let H be its subgraph. So if certain conditions are satisfied, then we can compress H into a single edge and label it, for instance, by A. So this procedure is actually opposite to replacement. So replacement removes an edge and inserts a hypergraph, and here a subgraph is removed and an edge is inserted. Well, for instance, in this graph, we can compress this orange subgraph into a single R-labeled edge with 4 tentacles. So now we introduce types and rules of hypergraph basic categorical grammars. So we need types. So we fix again a set of primitive types, and then we generalize the notion of division. And it is done as follows. Let n be a type, we call it a numerator, and let d be a hypergraph, we call it a denominator, such that exactly one of its edges is labeled by some special, fixed dollar symbol that is not used elsewhere, while other edges of d are labeled by types, also by types. Then we can, write this formal fraction n over d, and we say that it is also a type. Well, for instance, the following structure is a type. So it has a denominator. There is exactly one dollar labeled edge, and there is a numerator. It is a primitive type S. And of course, types can be more complex. So for instance, instead of this P, there could stand another type. And instead of this S, there also could be some other type. Well, and the main idea is the same as in the string case. So we are going to overlay denominators on subgraphs and compress them into edges. And this corresponds to the reduction law. Well, the main rule in the new formalism is the following. So let G be a hypergraph labeled by types, and let H be its subgraph. And let E0 be an edge belonging to H with the label N over D. So we overlay D on H. It is done by means of these two functions, E and V. Their definition is really close to the definition of graph isomorphism. The only difference is that we require that the only dollar labeled edge of D has to correspond to E0, this edge. And we, of course, do not require their labels to coincide because there is dollar and there is this type. So it is the formalization of this overlaying procedure. And then we, as I said, compress H into a single edge, and we label it by N, by enumerator. So this actually generalizes reduction laws. Well, for example, if we have again this type, and we have this hypergraph, there are many different edges, U, P, T. So E0, well, this denominator is overlaid on the orange subgraph, and then this subgraph that includes E0 and the orange subgraph is compressed into a single edge labeled by enumerator, that is by S. So this is how this reduction law works in the hypergraph case. Well, and then we define a hypergraph basic categorical grammar in the same way. So we say that it has, well, it contains of a finite alphabet S of a primitive type, sigma, and here is a primitive type S. And the essential part is a correspondence between symbols in an alphabet and between new types. Well, and then we say that the language generated by a hypergraph basic categorical grammar is the set of all hypergraphs G, so labeled by symbols of an alphabet, such that we can change these labels by corresponding types. This is the first requirement. In such a way that a new graph labeled by types can be reduced to S by applying several reduction laws. Well, for instance, we can again consider this E0 type. Well, now it is a part of a hypergraph basic categorical grammar. A corresponds to E0, B corresponds to S, C corresponds to P, and then we can, for instance, check the correctness of this hypergraph. Namely, we change labels by types, corresponding types, A with E0, C with P, as it is set here, and so on. And then we reduce this hypergraph to S. Well, for instance, firstly, we apply the reduction law to E0. We choose this subgraph, including this isolated node, as is here. And we reduce this to such a hypergraph. And we apply the reduction law again to this E0 and obtain S, as desired. Well, this looks well, somehow related to hyper-edge replacement grammars, but actually in an opposite way. So, actually there is a strong relation between hyper-edge replacement grammars and hypergraph basic categorical grammars. So the bridge between them is the following normal form. We say that a hyper-edge replacement grammar is in the weak Greibach normal form if there is exactly one terminal edge in the right-hand side of each production. And then there are two theorems that state that actually hypergraph basic categorical grammars are equivalent to HRGs in the weak Greibach normal form. So proofs of these theorems are actually very simple. Well, if we have a hypergraph basic categorical grammar, then we consider its types as non-terminal symbols, and if A corresponds to a type n over D, then we convert it into a production n to D, where we change this dollar label with A. And the other direction is has the same idea. Well, we consider now if we have a hyper-H replacement grammar in the Wick-Greibach normal form, then we consider its non-terminal symbols as primitive types, well, of the new formalism, and we convert productions of the form A to G into correspondences of the form A to this type, where A is the only terminal label on G. Well, this A label is usually called an anchor in the string case. Well, so as I promised, HBCGs and HRGs are actually well, strongly connected to each other. Well, it follows from these theorems that the membership problem for hypergraph basic categorical grammars is NP-complete. It is because, well, there is an NP-complete language that can be generated by a hyper-H replacement grammar in the Wick-Greibach normal form. And we, well, these conversion procedures are polynomial. And of course, this problem is NP. It is easy to show. So then, as I promised, hypergraph basic categorical grammars indeed generalize basic categorical grammars, and there is a natural translation. Well, we embed string types into graph types as follows. Well, primitive types retain, well, they retain, and they are also primitive types, and divisions are translated as follows. So a denominator here, well, it reflects the direction of division. So here the translation of B appears on the right, and here on the left. And this theorem states that if there is a usual string basic categorical grammar, and we well, change correspondences into correspondences with graph types, then a new grammar, which is a hypergraph basic categorical grammar, generates string graphs that are induced by words from L, from this language. Well, some words about structural properties. We have studied several well, properties. The first one says that it suffices to have one primitive type only, so we can construct an equivalent grammar for a given one GR, such that in its lexicon there are no primitive subtypes except for S, which appears here. Well, the proof of this theorem is just by substitution of primitive types by well, complex ones with big denominators. And another thing we studied is generalization of so-called counters for basic categorical grammars. So these are some invariants that are preserved by applying the reduction law. And they can be generalized to hypergraph basic categorical grammars in such a way that if one graph can be obtained from other one by applying the reduction law, then their counters have to coincide. For instance, we can calculate occurrences of primitive types on even levels of a type, so on the well, on the 0th level, on the 2nd level, and so on, with plus, and occurrences on odd ones with minus. And this is an invariant of application of the reduction law. Fine. Now I explain possible practical applications of hypergraph basic categorical grammars. Well, as I said, I would like to describe some, well, more linguistic phenomena using them. And again, we can consider types of hypergraph basic categorical grammars as functions that can, that take several arguments. And again, we can merge this new formalism with the lambda calculus and, obtain some semantics of graphs. Yes. And, for instance, we would like to describe certain linguistic phenomena that are related to the language of reduplicated strings. So this language is not, this language cannot be generated by a basic categorical grammar, but, it can be generated by a hypergraph basic categorical grammar. For instance, we consider the following example from the Russian language. It is a so-called cross-serial dependency. So we have a sentence: Оля, Петя, Вася финишировали первый, вторым, четвертым. Literally, Оля, Петя, Вася finished first, second, fourth. It is translated as Ola was the first who finished, Petya was the second who finished, and Vasya was the fourth who finished. And here, the noun Ola, it is a female name, is agreed, it agrees in gender with this ordinal number первый, first. As well as Petya, it is a male name, agrees in gender with the ordinal number вторым, second. As well as Vasya, agrees with четвертым. This is a cross-serial dependency, and it is closely related to the language of reduplicated strings. And here is a hypergraph basic categorical grammar that would, cope with such a phenomenon. We correspond types to masculine names, to feminine names, to masculine ordinal numbers. We correspond a primitive type that stands for predicate phrases. The same with feminine ordinal numbers. And there is a type T0 that corresponds to the verb финишировали, finished. We also assign semantic types to the syntactic ones. I won't explain this in detail right now. And then we take this string Оля, Петя, Вася финишировали первым, вторым, четвертым. We transform it into a string graph. Then we change labels with respect to these correspondence, and we obtain this graph. Then this type IF, it is here. Oh, sorry, it's here. It is overlaid. Its denominator is overlaid on PDF. Then we obtain this new graph with the Z labeled edge. We apply another reduction law to the type TM here. We overlay it on this PDM labeled edge. Then we obtain this graph. Simultaneously, lambda types are applied to each other, and we obtain certain lambda types on edges. Then we apply again the reduction law to TM, and this is the result. And finally, we apply the division inside Z and obtain S as desired. And moreover, we obtain these semantics that states that finish fourth Vasya and finish second Petya and finish first Ola, exactly as expected. So this is it. This is how hypergraph basic categorical grammars work, and this is how they can be applied to linguistics. Now to conclude, hypergraph basic categorical grammars, as expected, really combine basic categorical grammars and hyperage replacement grammars. We attempted to lift fundamental properties of BCGs to HBCGs, and we did this. We also showed how to generate some languages, string languages that are interesting for linguists. And we showed how to merge this with the lambda calculus to describe formal semantics of a hypergraph of a string, for instance. And what is also interesting is that actually the underlying mechanism of hypergraph basic categorical grammars can be formulated as a sequential calculus that deals with graphs. And this leads to an interesting, well, thought that now theorems can be considered as graphs instead of strings. So we used to thinking that theorems are usually strings, but here we can consider them as hypergraphs. And about future work, well, of course, we are interested in restricting hypergraph basic categorical grammars in order to obtain efficient parsing algorithms. So NP-complete is not so good. We are also interested in developing theory regarding to linguistics. And finally, we are interested in generalizing other string categorical approaches to hypergraphs. Well, we actually did some things in this area. We attempted to generalize the hypergraph-based lembic calculus, and well, something well appeared after our attempts. But it is a matter, of course, of another work. Well, this is it. Thank you for attention.
Okay, thank you very much, Tikon, for telling us what these categorical grammars are about. At least I didn't know. We have actually one question by Hans-Jörg Kreowski. He is asking, as you can read now, why do you require that the attachment nodes of a hyperedge are pairwise distinct?
Well, I just follow definitions from standard textbooks in order to show more connection with, well, classic definitions. But yes, I suppose it would be interesting to, well, allow nodes, well, to allow edges have loops, for instance.
Yeah, so I mean, what is your feeling? Do you think it's this restriction is essential, or do you think it could be lifted?
Well, it is an interesting
question. Of course, you can't give a definite answer, but I mean, from what you know and from your proofs and so on.
I would be really interested in generalizing this, and I suppose this could lead to some interesting results also. So I suppose I'll study this also.
Okay, so that's topic for future work. And there's another question by Frank Dreves. I guess it will come up in a moment. What does the fact that you only need one basic type translate to in hyperedge replacement grammars? Is it perhaps the fact that one only needs a single terminating rule? That's an interesting one.
So actually, that one not. So I don't understand this.
Well, is this assumption correct that you only need one basic type?
So not exactly. We have to have several ones because so for instance, we have to have a type that can be written only on edges with size 2, with size 3. So we have to have different edges. We have to have different primitive types, but so I do not think that this theorem actually states that we only need a single terminating rule.
Okay,
no,
so maybe that can be clarified in personal communication by email or whatever.
Yeah, I suppose.
Frank could contact you or you contact him. Okay, then it's 11:30. That's perfect. Thanks again, Tikon. And I suggest we continue with the last talk of this session. If the speaker is present. Uwe, are you there?
Oh, let me see.
I can see you. If you want to share your slides.
Yeah, it should go.
Okay, I can see your slides. So if you are ready, Uwe, please. So as you see, this is a joint talk by Uwe Wolter, Fernando Macias, and Adrian Rutel, multi-level typed graph transformations. So if you are ready, Uwe, please go ahead.
Yeah, I hope I have time to say at least 2 sentences about Michael. So Michael was the one that was headhunting me in 1991 after the wall came down to join the group of Hartmut. And one of the reasons was that I wrote my PhD thesis on algebraic specification based on partial algebras. So there's some line of things. Okay, I don't know. I'm not a very much fan of graph transformation, and I always try to avoid into this topic. But my two colleagues here, Fernando and Arian from the Högskole på Westland, always come with questions, and then I start to think about it, and that is one result of this collaboration. So what is it all about? So let's see, it should go, yeah. So, okay, what is the context and the motivation of the results I want to present here? So we are dealt with multi-level modeling hierarchies. So we have models, models organized in a tree-shaped hierarchy. So up above we have the most abstract models, down we have the most concrete models. And in this talk and in this paper, we consider only the underlying graphs, but you should keep in mind that models are also equipped with some constraints, diagrammatic constraints. But here we only deal with the underlying graphs of the models. And one main point with this hierarchy is that each model has a direct type in a model at a higher level. For example, here, I don't know if you see this, direct type of H1 is head that we find here. The direct type of hedge is part that we find here, and so on. And a specialty here, so to be flexible in this approach, we allow direct types to jump over levels. If you look at, for example, here, this arrow has no type on level 1, but has only a type at level 0. Yeah, so the direct type of Hess is e-reference 2 levels above. Yeah, so and further we assume that each element has a transitive type in the top model. So if we go, H1 is type is head is part is E-class. So part is a transitive type of H1 at level 1, and E-class is a transitive type of H1 at level 0. And some people may consider this model on the most abstract level as a linguistic meta model, but we don't focus on this distinction here. And in our applications and all the examples, we usually use eCore. Yes, here is just a graph, a unit graph as a default top model. Good. So what is the idea? So what do we want to have? So we want to transform models at the bottom of the hierarchy by means of multi-type typed rules. And the multi-type rule can be pictured like this. We have a left-hand side, a right-hand side, and then above we have a hierarchy that is local to this corresponding rule. Here we have this graph, and we just avoid to draw the uppermost graph, the top graph that is eCore at this moment. So here we have two level hierarchy for this rule. And what is a match? A match, we match this left-hand side with a graph at the bottom of a application hierarchy, and we have to match this rule hierarchy with the application hierarchy that is above the corresponding model we match the left-hand side with in the application hierarchy. And the whole point is to have everything kind of flexible. So a rule may be matched at this branch of the hierarchy, but we may want to apply the same rule at other branches of the hierarchy. So we have horizontal flexibility. And the other thing, the other demand of my friends was that we can stretching typing jumps as much as necessary. The background for this is that we may introduce afterwards other abstraction levels, some intermediate abstraction levels here for an instance or here for instance, but we still want that the rules are applicable, that we don't need to redesign the rules. Good. And this is one thing I also have to make clear from the very beginning. So we consider transformation rules as co-spans. Yeah, the left-hand side that corresponds to the from part, the right-hand side that corresponds to the to part. And in the middle, we have the union of both, of the left-hand side and the right-hand side. Good. Let's talk about typing chains. If you look at these multi-level, these hierarchies, then a path from the top to down is a chain of graphs. And all the types of the elements in this chain and graphs in this chain can be found correspondingly in one of the graphs in this chain. If we look now at so to get it a little bit more, let's say theoretically, so if you look now at the transitive closure of the direct type relations, then we can describe this typing by partial graph homomorphisms. Yeah, so from each graph in this path, we have a partial graph homomorphism to any other graph above this graph in this chain of graphs. And yeah, let's go back. So these, if you look at these here now, these are the instances that we want to transform later. Then we get the following picture. So this is a sequence of graph above the instance we want to transform, and we can say that this graph is multi-level typed over this typing chain. So that's a formal introduction of typing chains. Now I have to bother you at least with one definition. So what is a typing chain? Typing chain is a sequence of graphs and the family of partial graph homomorphism. What is a partial graph homomorphism? A partial graph homomorphism looks like this. We have two graphs. We take a subgraph of GJ and a graph homomorphism, a total graph homomorphism from this domain of definition into GI. This is a partial graph homomorphism. And then we have the following requirements. So every element in any graph of the chain has to have a transitive type in the top model. We have transitivity that can be expressed in this way. The composition of two typing morphisms is less than the corresponding direct type from G to I. And connex, it's maybe a little bit difficult to explain. This just means if I have an element in graph K, and we have two transitive types of this element, one in GJ and one in GI, and I is on a higher abstraction level, then the corresponding transitive type in GJ has to be also a transitive type in GI, and these two types have to be coincide. Good. Okay. Now we have typing chains, and now we can ask what are the morphisms between these typing chains. And please keep in mind, we want to have this flexibility of matches that we can introduce new intermediate abstraction levels. So we have somehow to stretch these typing jumps. And this is done by a function, so that from all the levels of these typing chains into all the levels of the typing chain H, so that the difference between abstraction levels can be equal or can be greater. And then we have a family of total graph homomorphisms from typing change G to typing change H, such that this diagram of partial graph homomorphism, that we have this inequality. If we go this way, then we get less than we go this way. This means that typing is preserved. And if typing is reflective, this means that the domain of definition of these partial graph homomorphism is an inverse image of the domain of definition of the corresponding partial typing morphism in H. Then we call it a closed typing chain morphism. So this means typing is also reflected. Yeah, we had this already in the talk of something similar in the talk of Harald today. Good. And of course, we can compose typing chains, and what we get is a category of typing chains. Yeah, I don't want to look through this now. Good. Now we want to apply multi-level type rules. First, I want to talk a little bit about the ideas, the intuition, and the objectives we want to have. So this is somehow the intuitive idea we have now. We have down here the underlying graph transformation rule. And these rules, all the three graphs in these rules are typed over, multi-level typed over the same typing chain that is locally adjoined to the rule. Then we have here now indicated application hierarchy where we want to apply this rule. S is a graph on the bottom of the hierarchy, and then this graph S is of course typed over the corresponding typing chain that is over S in the hierarchy. And what is now a match? We have to have a graph homomorphism from L into S. And this graph, and this is now the very important thing, we have to map this typing chain of the rule into the application typing chain. And this is a typing chain morphism. And these graph homomorphism and these typing chain morphism have to be compatible with a multi-level typing of L and the multi-level typing of S respectively. And the idea now is to take things easy. What we want to do is we use normal graph transformation rules. So it's maybe not the normal one, but the one we use. So we construct a push out in the category of graphs. So we get a result graph here. After this, in the second step, we take a final pullback complement. And the hope and the idea is that we get the typing of these two result graphs over this typing chain in the hierarchy for free. That is somehow we can, these typings are determined by these two constructions in the category of graph. Good. Okay, I tried a lot, and if one can really do this with these ideas. So this is the idea, this is a picture I have shown you until now. We have a typing chain here, and the idea is to have graph H. This is multi-level type. This means we have all these partial graph homomorphism into this typing chain, satisfying some conditions. But it turned out that this is not the adequate way to define multi-level typing. There are some internal things. You just cannot formulate adequate type compatibility conditions. So then I had a very strange idea. If you look here, so we have all these partial graph homomorphisms have a domain of definition. And what I do here now is just to list all these domain of definitions of these partial graph homomorphisms. And because we require that each element has a type in the top of in the most abstract graph in the typing chain. So the domain of definition of this homomorphism, this is the total homomorphism, this become H, and then we have all these domain of definitions, and here's a corresponding total graph homomorphism. And this picture looks very much like, nearly like a typing chain morphism. The only thing we have to be sure is that these sequence of subgraphs of H is actually a typing chain. And this surprisingly works. So we have this lemma. So I take any sequence of subgraphs of a given graph where H0 is H, and we can extend this trivially to a typing chain by just saying, okay, I have here two graph homomorphism, and in the middle I take just the intersection of HJ and HI. Yeah, and one can show that this is indeed a typing chain, and we call it inclusion chains. Yeah, because everything is given by inclusions. And now we are ready. Now we have a formal definition how we can deal with multi-level typing of graphs. So a multi-level typing of a graph H over a typing chain G is given by an inclusion chain H together with a typing chain morphism from H, from this inclusion chain into G. So the whole pictures I showed you before. So now we have it formal. So this is our way how now we can formalize what a graph transformation rule multi-level typed over a typing chain is. We have inclusion chains over for L, for I and R. So L is a part of I, R is a part of I. Then we have these multi-level typings here and these two triangle commutes in the category of chain. Then here we have now the instance that we want to transform. So we have a graph S with a corresponding sequence of subgraphs with this multi-level typing in the typing chain in the application hierarchy. We have a match down here from the left-hand side into the instance graph. And we have a typing chain between the rule typing chain, from the rule typing chain into the application typing chain. And this should commute. These match here down from the left-hand side into the multi-level type instance graph. This should be a closed typing chain. Good. And now, so we had this push-out construction, yeah, for the underlying graphs, and the idea is now that these push-out should give us a push-out for the whole inclusion chain in the category of chains. And this takes some time and to prove this, but luckily we have been able to show that this is possible. And the basic idea is because all these all the graphs in the inclusion chain here are subgraphs of L. All the graphs in this inclusion chain are subgraph of S. So we can actually apply this push-out construction on each level now. And fortunately, we get indeed a push-out in the category of chain. And then, so what we get by this push-out property is that we get this mediating morphism from this typing chain of D that we constructed into this typing chain in the application hierarchy, and everything commutes. So that's fine. That's actually exactly what we wanted. In the second step, we have this final pullback complement here. And now we have to get the typing. So we have to get these typing chain morphisms between these two inclusion chains. This is simply done by a reduction by pullbacks. So the typing of T is just obtained by a reduction of the typing of D. Then we borrow this arrow, we just take as a composition of these two arrows. So we get a multi-level typing of T over the typing chain and the application hierarchy. And then we have to construct this missing arrow here, these missing typing chain morphisms between these two inclusion chains here. And this, if you look in details how it looks like, this is actually easily done by simple composition and decomposition of pullbacks and graphs. So, good. What is the conclusion? Oh, now I was very fast. So what we have shown is that type graph transformations can be generalized to multi-level type graph transformations. And by improving the preciseness, flexibility, and reusability of transformation rule. This is the claim I would put for myself, is by introducing the category chain, we have been able to establish the necessary concepts, construction, and results in an adequate and well-organized way. As Detlef said before, so it pays kind of pays off to go this way. And one thing is so, and that's work that is going on now. So what our approach can easily deal with parallel, independent, multi-level typings of graphs and rules over supplementary hierarchies. Yeah, so maybe I go back. I have some minutes left. So we have this basic construction. Yeah, so and now we can think about, we do it for one typing of L and I and of this application hierarchy, but in parallel we may have all the instances in parallel typed over another hierarchy. Yeah, but because everything is based and induced by these constructions in the category of graph, we can just deal with as many supplementary hierarchies as we want. Yeah. And technical details and examples you will find in the paper and in the corresponding technical report. Okay, thanks for your attention.
Okay, thank you, Uwe. Right now, I don't see questions here in the live comments. I mean, I would have perhaps one just general question. So it occurred to me listening to your talk. So, you know, the literature, not very recent, but, you know, some years ago, there have been several proposals for hierarchical graphs and hierarchical graph transformation. I mean, it seems there must be some connection or relation. I don't think these relatively old approaches use typed rules, that's one thing, but I mean, just the structuring of these hierarchies and our rules are applied. Did you perhaps check any of these approaches? My feeling would be that your approach may just be more powerful and could embed these, but I'm not sure. Did you check that with any of those?
So what are hierarchical graphs then?
Well, it's intuitively, you know, you have like a normal graph, but at a node, let's say, or actually, for instance, in our project, where hyper edges and then certain hyper edges, you can zoom in, you know, there's another graph and then another and so on. So you have arbitrary depth of nesting, and then rules can be applied at these, but there's, at least in our old approach, there's just a global set of rules which can be applied anywhere.
Yes, I mean, I have to look at this. I'm not aware of this, or I had no, and one has to look seriously if you go back, because now I have to go back, if you have these pictures here. So what we usually work with, we usually kind of work with slice categories here. Yeah, and I have to check, I mean, how this is related to the sequences of graph homomorphisms. Yeah, so but yeah, it would be nice if you give us some references that I can check it.
Yeah, we can do that independently. Perhaps I'm also wrong, but I mean, in this picture, is it the case that certain modules here or whatever or models are kind of viewed as private to others or not? I mean, you have quite you don't seem to have many restrictions on the shape of this hierarchy here.
No. And as I said, so you want to. I mean, now we have a hammer plant and a stool plant, and then we may have a car factory, and so you just extend it horizontally and may introduce new. So yeah, but as I said, I should have a look at this.
Yeah, sure. Okay, thank you. Okay, so there seem to be no other questions.
Yes, I could have spent more time a bit. Okay.
You could have. You missed the chance, but anyway, we are close to the deadline. So thanks again, Uwe. Then question to Fabio, perhaps. What about the next session? Is the first speaker there? Has this been sorted out? Do we know how to continue? Graham is there. Then I think I can hand over to Lane as session chair, and I assume we can go ahead. Lane, do you want to take over? Your micro is muted, Lane. Okay.
Yes, here I am. Sorry for the delay.
Thank you. Please take it from here.
Thank you, Detlef, and welcome to our next speaker and to everybody who is listening to the next sub-session, which is on graph languages. And we will hear a presentation of Detlef, of a paper of Detlef, who just moderated the former session, Detlef Plum from the University of York, as well as Graham Campbell from the University of Newcastle, on confluence up to garbage, and it is applied to language reduction or graph parsing. So please, Graham, you briefly disappeared, but now you're there again. We are happy to listen to your presentation.
Okay, good. Can you see the slides?
Yes, I can see them.
Great, excellent. Okay, so I'm going to be talking about some joint work done while I was at York with Detlef. And we're essentially trying to answer this question. So it's, when does a graph grammar admit the deterministic algorithm for deciding membership? So to sort of just lay the foundations, for this talk, we're going to be only interested in DPO graph transformation, and we're going to have all our rules injective, all our matches injective, and only consider systems with phantom many rules. So I've included the definition of a graph grammar, just to remind you. It's just the usual definition. So we have a start graph, we have some non-terminals, and we're interested in graphs that are terminally labeled that are derived from the start graph using the rules. So because we are only considering injective rules, we have this first property which says that essentially if you can go forwards with a rule, you can always go backwards. And it's an if, no, if. So this then tells you for free that if you've got some graph in the language, that happens if and only if you can derive the start graph by going backwards with the rules, assuming that your input was terminated, right? But this process of going backwards to look for the start graph is not deterministic. So just because you terminate with some normal form that's not the start graph, you can't necessarily conclude that the G wasn't in the language. So it might have been a case of a different sequence of derivations that write the start graph. So sort of summarize this here. So as long as your inverse rules terminate, so in this inverse, I literally mean just flip the rules along. Okay, so if you have L, K, R, you just sort of swap L and R around, right? So as long as these reverse rules terminate, then you have non-deterministic membership. So when I say we're looking for deterministic membership checking, I'm essentially asking the question of when can we not bother to backtrack if we're going to implement this on an actual machine? When can we just derive as long as possible and then say, is the normal form that I have, the start graph, and that'd be correct. So there's sort of quite a straightforward example of when we can do this. So if you consider this grammar which generates the language of trees, so this shorthand with the ones, I'm just saying that this is the left hand side graph, and then it's also the interface graph, and then this is the right hand side graph. These ones telling you which nodes identified in the model, right? So if your start graph is this single node, and then your this is the rule on the grammar, then obviously this generates the language of the trees. And if you run this system backwards, then we're going to actually have a deterministic algorithm for testing if something is a tree. So this is because, well, 1 is terminating, obviously, and 2 is confluent. So we know that if we have something which was a tree, and we run it backwards, then we're guaranteed to get the start graph. And we know that if something was not a tree, we run it backwards, we're guaranteed to get something which is not a tree. So that's all good. So I sort of included these pictures at the bottom just to remind you about confluence and local confluence. So these pictures are not graphs, but this point is supposed to represent a graph, and this is meant to represent 0 or more derivations, right? So it's just saying that you take some graph and then you derive arbitrarily far away, and then you can always find some common reloads. And then local confluence is saying, well, I'm only interested in going one step away. So before I go any further, I just want to remind you of a few standard results about confluence. So, well, and termination. So testing for termination is undecidable. So is testing for confluence, even if you given termination. So useful to bear in mind. And well, everything is not completely hopeless, is the point of this next level. It's called known as the critical pair lemma. So I mean, we can't hope to have a decision procedure, but we can have sufficient conditions. So this lemma is saying that you have local confluence whenever all your critical pairs are strongly joinable. So I'll explain a little bit more about what that means a bit later. But yeah, this result is going to be something that we're going to be looking to generalize. And this is also this classic result, which is confluence and local confluence coincide whenever you have termination. So the point is that if you have termination, then this lemma is actually telling you about confluence and not local confluence. So it's actually going to be quite strong. In the tree example, we had confluence and termination giving you a deterministic algorithm, but confluence is really quite a strong thing to require. So this example should demonstrate this. So there's this language class called the extended flow diagrams, and it's essentially just some sub-language of the semi-structured flow diagrams. And we can define the language as being generated by these 5 rules. Well, I mean, you can think about them as graph transformation rules, where these squares are nodes, or you can think about them as hypergraph transformation rules. It doesn't really matter. So essentially, we have this graph is going to be our start graph, and then these are going to be our 5 rules. And again, we can consider what happens when we turn the rules around. We try and run them backwards as long as possible to determine if something's an extended flow diagram. But we found we run into a problem. So this graph here in the middle, we can derive one step away using the inverse rules, but we end up with 2 graphs that are not joinable. So these inverse rules are actually not confluent. But it's going to turn out that we still have deterministic membership checking. So this will all make sense by the end of the second section, I think. But to sort of explain what's going on here, why this is going to be the case. So I have a little picture here. So this is the classical graphs of a signature for this graph. This is the language of all. It's meant to say EFDs, sorry, extended flow diagrams. And so consider you start with some graph which is not in the language, H0, and then you do a derivation using the inverse rules, and you do a derivation using the inverse rules, and you keep going, and eventually you stop somewhere. Well, you've always stayed outside of the language, right? And the same is the case when you're inside the language. Whenever you've got an extended flow diagram and you apply one of the inverse rules, well, you stay inside the language. So being confluent is kind of too strong, because so this conflict here can actually only occur outside of the language. That's the whole idea. So the conflicts outside the language don't matter as long as you can't stray inside the language with the rules, right? So not being confluent out here doesn't matter. So as long as you're confluent inside here, that's going to be the important thing. So as long as I derive as long as possible and get the start graph, that's fine. And as long as I derive as long as possible and get not the start graph here, that's what we want. So not the start graph is weaker than saying some fixed graph, right? So if I just say this again, slightly more generally, so we're going to define this notion of confluence up to garbage. And that's just going to be confluence, but only when we consider start graphs that belong to some language D. So we're only considering these diagram pictures, right? They start from some graph in G, right? Yeah. So the idea is that we're going to have deterministic membership checking from termination plus confluence to garbage, right? This is basically the result that we're interested in. So, yeah. So this proof is pretty much just what I described for the extended flow diagram case. So as long as you're confluent here, then you're going to end up with S. And as long as it doesn't matter about confluence here, as long as you don't end up in here. So this is exactly what this is saying. So yeah. So then the question is, well, we're not really going to answer the question of how do you test determination. I mean, you can't, and even sufficient conditions are sort of outside the scope. But we are going to ask, how do you test for confluence up to garbage? This is essentially going to be a generalization of that critical pair level we saw before. So if I just remind you what a critical pair is. So you've got some graph transformation system, and then critical pair is going to be some parallelly dependent pair of direct derivations. So you've got your start graph, you've got one of your direct derivations, and you've got your second direct derivation, and you want the two matches to be jointly surjective. That's the same as saying that G is just the overlap of, not the overlap, the union of the images of the two matches, right, on the left-hand side graphs. And in general, this won't be disjoint, right, because we want dependence. So this will always be not disjoint. And then we have this extra condition here, which is just to throw away the pairs that really don't matter. So if you have two rules that are the same and the matches are the same, well then it's sort of just degenerate. You have both of your derivations being the same, so you're obviously going to end up with joinability. So we're not going to care about those cases. So our generalization of a critical pair is going to be a non-garbage critical pair. So you've got, again, some graph transformation system, and you've got some set of graphs. So we're going to say that a D non-garbage critical pair of the system is a critical pair such that the start graph can be embedded in some graph in D, right? So this is the same as saying that G is in the subgraph closure of D. So as long as this D hat is decidable, then we can effectively enumerate all the non-garbage critical pairs. You just enumerate the critical pairs in however way you do that, and then at each point you just have a test: is the start graph garbage or not, right? And you can just throw away the ones that you don't want. In order to present this generalized version of the critical pair lemma, you can't see my cursor. That's
yes, Graham. We don't really see it either very clearly, but yeah, I don't know if it's critical for you.
I think we've passed the point where I needed it. I don't know if I need to go back to explain anything. I mean,
I think you should maybe just go ahead.
Yeah, so the point where my cursor would have been useful was either pointing at the yellow or pointing at the blue. But I think that hopefully was clear enough.
Yeah, you can briefly repeat if you wish.
I think it's okay. So right. So yes, I was here. So strong joinability. So strong joinability is essentially a stronger version of joinability. So you call a critical pair strongly joinable if it's joinable, but without deleting any of the persistent nodes, and the persistent nodes are identified in the reader, right? So persistent nodes. So persistent nodes are essentially those nodes that exist in both H1 and H2, right, from G. So it's those nodes that matter. So it'll make a little more sense when we see the proof. So it's essentially you don't want to be in a situation where you delete the node which was needed when you embed a critical pair in context, right? Because you may be in a situation where you delete a node which may have had extra edges, so the dangling condition will fail when you try and embed, right? So our generalized critical pair lemma is essentially saying that you only need to check the D non-garbage critical pairs for strong joinability in order to give you local complements on D. That's the idea. So it's we're able to ignore some critical pairs. So the proof is, well, what must we do? We must check that all pairs that look like this can be joined. So this is just the definition of local confluence up to garbage on D, right? Just saying that all critical pairs that have G and D can be joined. So the first case is quite straightforward. So if it's the case that this pair direct derivations is parallelly dependent, you can't see my cursor here. Imagine I'm pointing at the critical pair. Then by commutativity, you're done sort of just straight away. And then the second case is you're parallelly dependent. But then what we're going to do is we can use clipping to so I'm pointing it now at the diagram, which has the S and the T1 and the T2. So you're pulling out this critical pair using clipping, and then from the definition of garbage, well, you know that this S in the critical pair must actually be embedded must be embeddable in some graph in D, right? If it's embedded in G, which is in D. Then our assumption was that such a critical pair is strongly joinable, and then the conditions of strong joinability allow us to then use the embedding theorem to get what we want. And this last little bit at the bottom, it's not too hard to show that is actually a bijection. So the M1's M2 morphism. So yeah, we've got the result. So remember, we wanted confluence on D and not just local confluence. And the sort of classical Newman's lemma doesn't quite generalize. So just because you have termination and you've got local confluence on D, that doesn't give you confluence on D. You actually need an extra condition, which is that you stay closed inside D. So whenever you derive from some graph, you've got some graph G and then you apply T. You want to stay. If D is inside, so if G is inside D, you want to stay inside D, right? So if you have this extra condition of being closed, then you can do induction. You can get a result. So if you weren't closed, then you couldn't imply the induction hypothesis to say this H prime 1. This H prime 1 might not be in D. So yeah. I mean, you can actually come up with counterexamples that are quite straightforward to show the unique closeness. So yeah. So if I sort of just summarize where we're at. So you want to check the confluence of the garbage. So you've got some graph transformation system T. You've got some language D. And well, first you want to check that T is terminating and D is closed into T. Once you have that, you can then generate the finitely many non-garbage pairs. And then you can check if each pair is strongly joinable. So this process is always going to terminate because, well, you know that T is closed into D and terminating. So it's just essentially telling you that you're only going to have finitely many successive graphs from any given graph, right? And you've only got finitely many pairs. So you can certainly produce all the successive graphs and then just brute force check whether they're isomorphic and satisfy this strong joinability. And then, well, if they're all strongly joinable, then you have confluence on D. If you have a pair which is not joinable at all, you've got a direct counterexample to confluence up to garbage, right? And then, as is usual, then you have this third case where you have all the pairs joinable, but not all of them are strongly joinable, and you can't conclude anything from that. So you don't have a counterexample to confluence, and you don't have a proof of confluence either up to garbage. I mean, these graphs that are not strongly joinable, I mean, as a human, you can often look at them and guess by adding context and then trying to produce a non-joinable example. But yeah, this can't be automated in general, right? Because yes, confluence is undecided, but confluence is undecided. So I just want to return to this example and then show one more example, and then we're almost done. So recall we have this non-joinable pair, this extended flow diagram example. So, but this start graph is garbage, so it can't be embedded in an extended flow diagram. So we can essentially just throw away this pair. It's a garbage critical pair. And well, I've not included all the other critical pairs in the slides, but you can check them all, and they're all going to be strongly joinable. So, and we have termination because all the rules were size reducing. So we actually have confluence of the garbage by using this process, which is correct by this this, right? So we've answered the question for this example. So we know this has a deterministic recognition algorithm, and you get it for free just by running the grammar rules backwards. Okay.
Graham, you have short 5 minutes still. Okay.
So final example is going to be series parallel graphs. So these were introduced by Buffin in 1965, and they're defined to be the smallest class of graphs clothed under parallel and sequential composition containing this graph P. So parallel composition is you essentially take two graphs P and Q, and you disjointly union them. You take a disjoint union, and then you identify the source of both and the target of both, right? So essentially just putting them together and then plugging the two ends in, right? And then sequential composition is you plug the source of one into the target of the other, right? And although Duffin wouldn't have phrased it like this, he essentially showed that actually this process of composition, it's enough to only consider it locally. So a graph is series parallel if and only if it can be generated from P using these double push-up rules. So if you turn these rules around and ask the question, are they confluent or determinating? Well, the answer is yes. But the thing that starts to go wrong if you're interested in adding labels to your graph. So even if you have a label alphabet for the edges with two distinct symbols, let's say A and B, so these would be the sort of obvious rules for. I've written them the other way around, so we're going to be interested in reduction, right? So these are the obvious reduction rules for that language. I'm going to call the language of labeled series parallel graphs. We end up with these pairs that are not joinable. So just by adding labels, we've broken confluence. But or it's not lost, because this graph and this graph are cycles, and series parallel graphs are cyclic. So there's no way you can embed one of these in a series parallel graph. So we can conclude these two pairs are garbage. So we can throw them away. And then now we're just left with looking at the rest of the pairs, which are going to be strongly joinable. So we have confluence up to garbage again, and termination. So we have deterministic recognition. So yeah, that's good. So I just want to say a few things about how we can make these results more general, and then some future work, and then we're done. So I only showed you examples that used grammars without non-terminals, but the process applies in general. So you instead of taking D to be the whole language, you take it to be the language, but also including the graphs that are not terminally labeled. Right? So our generalized Newman's lemma, that works for any abstract reduction system. It's nothing special about graphs here. If you have closeness, yeah, it works in general. And then this generalized critical parallel also works in more context than what I showed you. So it works for hypergraphs as well as graphs. And you also don't need injectivity of the right-hand part of the rules. So that's fine. It also works for any adhesive system and for the usual restrictions. Although the proof I showed you won't work. So the proof in my BSc thesis for the theorem does generalize pretty much immediately to this adhesive case. So that's the proof that you look up for that. And then in this setting of relabeling, so this is sort of interesting. So relabeling and root nodes are sort of very useful for GP2, which we saw in GCM. And this system's not even M-adhesive. So it's sort of interesting that actually we have a critical parallel for something which is not M-adhesive. This is an technical report. And then some future work. So we haven't looked into usefulness of classification of non-garbage conflicts, or connection to essential critical pairs, or connection to graph satisfying negative constraints. And we don't have sufficient conditions for deciding membership of subgraph closure. So remember I said that I needed D hat to be decidable. It's not obvious. Say you've got some grammar for D, nice and decidable, but the subgraph closure need not be. So we don't really understand what the relation is there yet. And there's also a relationship between confluence modulo garbage and confluence after garbage. that's to do as well. That's everything I've got to say.
Okay, thank you very much, Graham. I don't see any live comments for the moment. Can you outline a bit how the language D is supposed to be defined? At some slide you said, or you presented, that you can use a grammar for doing that. What would be other possibilities to do that? Do you see some connection with using constraints to do that? And maybe then, yeah, the connection to application conditions and rules would be obvious.
Yeah, it's not so clear. So we haven't actually considered any examples where we're not using a grammar. But I left it in there because, I mean, this process works even if you don't have a grammar for D, as long as D is specified in some way. So yeah, I suppose one of the examples I had in my head would be like some sort of logical formula or something. We haven't actually.
Yeah, some logical formula or maybe nested graph conditions.
Yeah.
Then. Yeah, I think there should be a connection, or I assume there should be a connection then, even with then, yeah, because you can translate constraints into application conditions for rules. Maybe you could even then connect to the theory of critical pairs for rules with application conditions. That might be also interesting to check. And with respect to implementation, did you think of implementing this generalized theory, or
So the tricky part is overcoming this membership problem for subgraph closedness. So just because you've got some grammar for D, it doesn't mean you know how to detect if something can be embedded in D. That's the problem. So that, yeah, if we can find sufficient additions to be able to compute membership of D hat, then we can implement it. This is sort of sticking point.
I guess when you define D with constraints or graph condition, then closeness would be related to checking invariants for rules. So when the invariants are graph conditions, then there is some work on doing that. So maybe there is a chance then.
Yeah, I mean, I should maybe comment that 12ness is undecidable too. So.
Yeah. You have to make some restrictions, I guess, in practice to make it work. Okay. And maybe some very last short question. You talked a bit about generality and adhesiveness. Can you explain or outline a bit if your approach works also in that context?
Well, I haven't checked adhesive, but I imagine it would work. So adhesive, essentially, you can just show that it's the non-garbage pairs are complete in a sense, and then the rest just goes through as usual. So it's not too much work. But we decided to include a more direct proof, which doesn't generalize to adhesive this talk. So.
Okay. Yes, time is up. But thank you very much for your talk, and we switch to the next talk of Bertolt, which is also related to graph parsing in the setting of hypergraph grammars, I think. We are going to hear a presentation of a Swedish-German cooperation. Bertolt Hoffmann will give the talk, and Frank Troers and Mark Minas are the co-authors of a paper called Graph Parsing as Graph Transformations, Correctness of Predictive Top-Down Parsing. So if you are ready, Bertolt, we are as well to listen to your talk. We can't hear you yet because you are muted.
So hello, everybody.
Yeah, now we can. You should still share your slides, I think.
Yes, I'll try, but it doesn't work.
It will.
So there's crazy options.
Yes, share screen, and then the full screen is the easiest option.
I
I think.
know. Full screen. Yeah, but I can't. So the option is great, so I can't do it. But the other is also great. I don't know what happens.
You could try another browser.
I'm using Google Chrome. I think this
work,
was. Now I can.
It's okay.
Oh no. This is completely different. Wow, but that's crazy. It worked.
It worked before.
Yeah, it worked before. Yeah, so I couldn't even. I can share this a file. Okay. So better than nothing. Do you see? No. You don't see it, huh?
No, we don't see your slides yet.
Don't see my slides. All these sections. Yeah. Yeah, sorry, I have no idea because at least the file is there, so you will have to cope with the borders and so on. Okay, excuse me for the delay. Yeah, and thank you for the introduction, Lane. Yes, we are continuing our efforts to efficient graph parsing for hyper-edge replacement grammars and actually also contextual hyper-edge replacement. But I won't talk too much about contextual hyper-edge replacement today. And so I just made a small, silly drawing concerning the motto of my talk, and to put it very short, it's just order your edges, order the edges that you want to pass. And I think it will be clear in what this means. Okay, so graph parsing, and I just talk a bit on hyper-edge replacement grammars as the object of being parsed, is a well-structured mechanism to generate graph languages. And it's nice that they are context-free, because context-free languages have nice properties. But unfortunately, for HR languages, parsing is not that favorite, because there are HR languages that are MP complete. And so there will be no general parsing algorithms for HR languages that is efficient. However, we found out that we can do efficient parsing for some suitable subclasses. And that's what we have worked on over the last couple of years. And so this is our construction side. So first of all, we have two parsing techniques, all oriented towards string parsing. PTD is a top-down parsing algorithm tailored after the LLK parsing technique for string grammars, and predictive shift reduced parsing is tailored after the LRK string parsing technique. This has not only been discussed theoretically, but Mark Minas has implemented these parsing techniques, among others, in his graph parser distiller, which can be downloaded at his university. And I mentioned it before, these parsers also work for contextual HR grammars. But as I said, also, I will not talk about that today. So today's topic is rather correctness of graph parsers. In our first definition of PTD, of course, we also considered correctness and argued and had some arguments why these are correct, but we never have a real correctness proof. Recently, we did this for PSR, which is a bit more complicated. And there it turned out that the proof is really very complicated. And so we thought, oh, maybe we should just try to prove PTD in another way. And our idea was to use graph transformation to describe the parser and hope that this will make the correctness proof easier. Since an easy correctness proof is very important for us because we want, for instance, to relate PTD with PSR. And if the proofs are very complicated, this will be a very tedious job. Okay, so this is the construction side. And let me start by just recalling hyperedge replacement, and very briefly, because many of you will have heard of this. So I just give an example and explain the threads later. So an HR grammar is just, in this case, it shall generate trees. It has symbols for the serving as edge labels. Some of them are non-terminal, and they have productions, and productions have a hyperedge basically on the left-hand side, and they replace it by a hypergraph when they are applied. And in this case, we have just 3 rules. The start rule generates a terminal root edge, this half circle, and the T non-terminal then generates branches in the recursive case and just terminates in the non-recursive take. And the start graph is just the left-hand side of the first production. And this generates threaded trees. And this is because, yes, these gray nodes and the gray lines, they are additional tentacles of the hyperedges that just serve to help the parser. They are not relevant for the language being derived. So but let's see an example on the next slide. Here again are the productions. And so we derive as usual, starting with the start symbol, applying the start rule, then applying the recursive rule over here, then and so on and so on. What we end up with is a terminal threaded tree, and you see the white and black part is more or less a tree, but the edges have extra threads that order them in a linear fashion. And this is what I mean by auxiliary edges, because they are not considered relevant for the language of the grammar. Just they are relevant for doing the parsing. Okay. So now we have to see how can we define general top-down parsing which is inefficient due to non-determinism by graph transformation. And so just a look back to the string case, and it's very similar in our case. So context-free parsers are stack automata, and how do these automata work? So they start with some initial configurations. These are initial configurations contain the input, and in this case I say it's a graph G, and then they perform a sequence of parser operations on these configurations until, hopefully, they come to an accepting configuration that tells the parser that he had success. And so this is not easy to imagine that this can be done by defined by graph transformation. So what do we have to do? We have to represent the configurations as graphs, and we have to define the parser operations by graph transformation rules. And in the case of top-down parsing, there are two kinds of transformation parser operations. One is to expand a production in order to construct a tentative derivation of some graph. And the other one is to match a terminal edge in order to make sure that we do not just generate some derivation, but a derivation of the input graph that we have. But let's see how this looks like more in detail. So a configuration graph has several constituents. The first three are the red input, this is the green part here, and the stack, which is just black in the example. And this is a threaded subgraph of the configuration. And then we have the unread input of the configuration, which is drawn in red here. And this is an unthreaded subgraph because, of course, the input of our parser is not threaded. That would be too easy. So the input is just an ordinary graph. And now we have additional information in order to control the work of the parser. We have one unary edge type, unary edge with this black square, which is the reading head of the parser or the top of stack of the automaton. Then we have these double-lined circles, which flag the red nodes of the input, and we have this crossed out circles that flag the unread parts of the input, the unread nodes of the input. And to make the drawing more convenient, we just indicate these edges by drawing the nodes accordingly. And so now, how does an initial configuration look like? Oh, it's just it just consists of the stack containing the start symbol and the input we are going to pass. And accepting configuration, how does that look like? Okay, there the stack is empty because you see the black square is at the end of the thread, and all of the input has been read and is green. So these are the data of the stack automaton, and now let's go to the operations. I start with the match operation, which is somehow a bit more complicated. So this operation will always try to match the topmost terminal edge on the stack if the topmost edge is a terminal. And so here we see the left-hand side of the transformation rule. We have an edge E, that's the one drawn in black on the stack, and it's on the top of stack. You see it on with the black square. And what we need to, for this match operation to apply, is an unread edge that shares the read nodes. In this case, it's the node K, and which does not share the unread node, it's G, with the node on the stack, which is called M. And if such a situation occurs, then we can do the following. We delete the unread edge, the red one. We identify its formerly unread node with the node that occurred on the stack previously, and we remove this edge because it's now being matched from the stack, and put the stack top to the right. So it's no longer on the stack, but it's on the read input of the parser. So this is one match rule we need for this example. The next one is for the root edge, and this is done similarly, only this edge has just one attached node that is unknown when we try to match it, and so the match rule looks like this. In theory, we would need also further match rules, maybe, for instance, for a binary edge where both nodes are known or none of the nodes are known, but this is not the case in our example. So the next operation, or the next kind of operation, is the expansion operation. There, the topmost non-terminal edge on the stack can be handled, and of course just if the topmost is at non-terminal. And this looks like shown here for the three rules of the tree grammar. And what we do is just we extend or flag certain parts of the threaded production, namely to indicate the top of stack, because expansion is always performed for the symbol on top of the stack. And also we distinguish read and unread nodes in the productions. And that's all. And so in summary, we see that our parser graph transformation rules are more or less ordinary DPO transformation rules. All nodes of the left-hand sides are preserved in our case, so we need no dangling condition. The occurrence of the left-hand side must be injective, the occurrence in the host graph to be operated on. And in some cases, the nodes of the left-hand sides are merged on the right-hand side, like here for the thread nodes of the terminating tree rule. Okay, now let's see a sample pass with these operations. So we start with the initial configuration. We apply, in this case, because it's a non-terminal on top of the stack, we have to apply an expansion. Then we have to apply a match in order to match the root node, which is now on top of stack. Then next we have to apply an expansion rule because a non-terminal T is on top of stack, and so on and so on. And in the end, we get our accepting configuration. Everything has been read. The stack is empty. So this is how it works. Sorry. Now for the correctness, we just say that R of gamma denotes the set of match and expand rules for gamma. And we also say that tilde C is the threaded subgraph contained in the configuration. That means all the graph, the configuration except the unread input. And then we have a lemma saying that if we do a match from one configuration to the other, the threaded subgraph is not changed because we just move the stack pointer. For an expansion, it holds that we perform a leftmost derivation step with the threaded production because we insert the right-hand side of a production for the left-hand side. And this helps to show in a rather straightforward way that for every initial configuration and any accepting configuration, there is such a parse whenever, if and only if the language is in the graph is in the language of the grammar. So this is for correctness. And of course, the other thing would be termination. And there we have the usual result, also known from string grammars. All sequences of parser steps with our rules terminate unless the grammar has left recursive non-terminals. This would be the case, for instance, if the left-hand side of the recursive term tree rule would start with a non-terminal t, because then we could expand t without making progress in the input, and the parser would not terminate. Okay.
Sorry, Bertolt, you have short 5 minutes still.
Okay. So now the parser is inefficient due to non-determinism, and this has two reasons. One is expansion. If we are in a situation to expand a non-terminal t, for instance, in our example, we can use both rules, and we don't know which one to reuse. And so in this case, we just use this one. The other source of non-determinism is the match, because here, for instance, in this middle situation, we have to match a binary edge, but we have two candidates that are suitable for this case. In this case, we decide for the lower one, but we could have decided equally well for the other. And so, yes, in DPO terms, these are just critical overlaps of the rules. And so what happens with this general top-down parser, whenever it gets stuck, that is, it's not in an accepting configuration, but cannot continue, then backtracking has to be done, and this is very inefficient. So what is the idea of predictive top-down parsing? This is again borrowed from the string case to some extent. We analyze and restrict the HR grammars that we want to process in two ways. First, we consider look ahead into the unread input in order to decide which of the expansion of the productions to be expanded are promising in the sense that they will lead to a successful parse. The other one is for the terminal the matches of terminals. We just make sure that the grammar is built such that every suitable terminal edge fits if we want to match it. And so this leads to the definition of PTD parsability, and just by saying that free edge choice must be given, and we must have predictive expansion rules that use the look ahead in order to decide uniquely which rule should be used in an expansion. And if an HR grammar is PTD parsable, then the parser is correct with the predictive expansion rules. I now come to the example to show you how they look like. So this just concerns the two rules for T, because there we have a choice between two rules when we expand T. And so if we want to terminate, then there should be no further edge hanging on this node where we have the non-terminal T. And in the other case, if we want to, in order to expand the recursive rule, there should be such an edge. And so these two conditions, which are application conditions, just ordinary application conditions in the DPO approach, we can decide which of the productions to be expanded. So free edge choice is a bit more difficult, so we have to sufficient criteria to be checked on the grammar. I will not go into details of that. And so in our case, trees are parsable with PTD, so free edge choice holds as well. And now with PTD, the great advantage is that whenever the parser gets stuck, it's sure that the input graph is not correct. So we can issue an error message and we are done. We do not need backtracking. Just to give you an idea what are PTD parsable HR grammars, we have one result concerning chain grammars that can be derived from context-free string grammars. And there the result is that SLL1 grammars are all PTD parsable. So in a sense, we lift a certain way of top-down string parsing to hypergraphs. And also palindromes are parsable, which is interesting because it is known that there is no deterministic stack automata parsing palindromes in the string case. And this is due to the fact that we are not so biased with respect to the direction in which we read edges. Okay, and for graph examples, I just mentioned two of them, nice Schneiderman grammars and Blowballs. Okay, concluding, we have shown that PTD parsing can be defined by graph transformation, and that the correctness proof is rather straightforward due to the close relation between the parser definition and the definition of hyperedge replacement grammars. And even the extension to contextual HR grammars is relatively easy, but I won't explain this today. So future work is to do the same for PSR parsing and to study the relation between the two parsing algorithms. And this is a long-term aim to enhance these contextual HR grammars and also grappa for model definitions, which do have further features like types, attributes, path conditions, and so on.
Okay.
And of course, this last point, convince people to try Mark's grappa. And okay, thank you. Sorry for taking.
I will have it.
Okay.
Okay. Thank you very much, Bertolt. I do not see any live comments for the moment. Just one question from my side, maybe. What about the practicality of the approach, so to say? So how does a user, what hurdles does a user have to take to be able to use the approach? So you need to somehow have this property of predictive top-down parsability. And how difficult is it to get it?
Yeah, so for the moment, the implementation in grappa just has a textual interface. So you define your HR grammar with a textual interface, and all the rest is automatic. That is, the parser checks the look-ahead condition, the free edge choice. It checks other conditions that might lead to a parsing failure, and so it answers you. It's PTD parsable, and then it generates a parser, and so it's like in the string case, it's a complete parser generator.
Okay, and the look-ahead condition, how does it arise?
Yeah, this is as in the string case. You just look in which configuration you could be if you want to expand a rule, and then you calculate what can come as terminal symbols if you proceed, and you make an over approximation of these symbols that can occur, and so you end up with a set of edge patterns that may occur if you choose this expansion. And for the other expansion, the same holds, and in order to be predictively possible, there should be some terminal edges that make the distinction. And in our example, it was just the presence or the absence of a certain edge pattern. It can be more complicated. So there's and we have even a more complicated calculation of look ahead than in the string case, because we don't have linear orders in our terminals. But that's
So the application conditions will need to become more expressive to be able to handle more examples, I guess.
Huh? Sorry.
The application conditions that you use
so
for the look ahead.
I hadn't mentioned this. So in general, it will be an OR of certain edge patterns, positive or negative. So that's the general structure. In the other way in the more complicated way, we can even count how many edge patterns can appear in one case and in the other. But that's even more complicated.
Okay. Okay, if there aren't any live comments, then I thank you very much for your presentation, Bertolt.
Thank you.
And we switch briefly. We take a few minutes to answer some questions of the previous talk that we missed of the live comments. Sorry for that. That live is available for answering since he was also
Unfortunately, my co-author and presenter disappeared, but anyway, I can say a little bit. So one question here, we can see it by Frank. Do you have or envision any complexity results under reasonable assumption? Maybe that would be future work as well. On the later, definitely yes. So in general, okay, so just a few comments. I think it's difficult to say something there. So one thing is on the generation of critical pairs and the confluence up to setting. Of course, an extra step is checking whether the middle graph of a critical pair is in the subgraph closure. So first, that has to be decidable at all, as Graham pointed out. And then, of course, in general, if it's a complicated language, it may have an expensive recognition algorithm itself or detection algorithm, so that would go into the complexity of generating critical pairs. Of course, that is a kind of, you may view that as a pre-processing step. Once that is done, once and for all, you have the critical pairs. Then for the reduction itself of the checking strong joinability, well, I mean, in the two examples that Graham showed, flow diagrams and series parallel graphs, both series parallel and labeled series parallel, the reduction rules are size reducing, which means our non-deterministic reduction algorithm, one can say at least, will always terminate in a linear number of rule applications, okay? Of course, that is quite an abstract complexity model. It doesn't take into account the cost of matching. So there we delve into the general area of what to do to get constant time matching. I mean, we have a little bit of work on that in the context of our language GP2. So we would use rooted rules. So it would make sense to get fast reduction also here to use rooted rules. Of course, then one has to check that the rooted rules obey the condition, but in principle, it's possible. But for instance, for the two examples, flow diagrams and series parallel graphs, we looked at it, at least for series parallel, and we labeled series paragraphs, and we don't know how to put the roots there. So it's a problem on its own. If we could, then we had a real linear reduction algorithm in the traditional complexity sense, but that's open. Maybe that's enough on that one. And then there was the one by John Crevine. Yeah, what about SPO? Can we do the same? So I must admit, I don't recall the full SPO critical pair analysis. One thing which Lane reminded me of is definitely that you usually have many more critical pairs because simply the dangling condition not there. So you will have many more, so you have to consider that. Otherwise, I mean, genuine problems in our approach, I wouldn't expect, but this is really just my gut feeling. One has to check that carefully. That's all I want to say.
Frank just replied and is happy with your answer.
Good to see.
Yeah, that was nice that we could still handle this just before lunch. I wish you all a nice lunch, also if we can't have it together, and which is a pity. But yeah, next time, I guess. And we will pass now to Timo for some closing words, I guess, of this session.
Thanks, Lynn. Thanks to all the speakers and session chairs of that morning session. Yeah, which is closed now. I think Lynn already said everything. So have a nice lunch break. Don't forget your lunch tickets. The green one for Friday. Yes, we'll be back here at 2 p.m. with the afternoon session. With still 2 very interesting sub-sessions on system modeling and the tool presentations. And also do not forget, afterwards, we will have the short closing session with a brief awards ceremony. Well, the ceremony. And if you want to do a little bit more socializing, we will set up a Zoom meeting. This has still not happened yet. But we will announce it as soon as we have it. Okay, so have a nice lunch break and see you at 2 p.m. Thanks.